Good morning to both of you. We start with a polar curve. R equals sine 2 theta plus 2. Looks a bit like a monkey nut or something like that. It's defined for all values of theta because R is always positive. If you think about that, that makes perfect sense because sine runs between -1 and 1, and because I'm adding 2 to it, I've definitely got a positive value. In fact, it reaches its maximum value when sine 2 theta equals 1, which will be when theta equals 45 degrees. Hence, if I come out on a 45-degree angle, I'm as far out as I possibly can be, and that point there would actually be 3 away from the origin. It's its shortest distance out here, and here would be 135 degrees, because if you double 135, you get 270. And sine of 270 is -1. Take 1 off the 2 gives you 1, so that's a distance of 1 out. Anyway, that's not why I've got this graph up here. I've got this graph up here to explain the topic of tangents to horizontal and vertical tangents to this curve. In other words, line that just touches the curve that is vertical, there, and lines that just touch the curve horizontally, which would be there and there. Tangents to the curve that are vertical and tangents to the curve that are horizontal. If you've read the notes, you'll have seen this topic, but I thought I wanted to go through an example with you, this one specifically, just to show you how we find the coordinates of where those tangents actually are. Because it's not, I chose this graph because it's not immediately obvious what angle you would be on when you hit that point there and that point there, which are the two values that we're looking for, and similarly that point there and that point there. So that's what we're going to do, is we're going to use the curve r equals sine 2 theta plus 2 to find those tangents. So we're going to move that out of the way and just write down the equation of the curve again. So it's r equals sine of 2 theta plus 2. Okay, let us begin. So we're going to do the vertical tangents first. So I'll just put a subheading, vertical tangents. Okay, and what we need to do is we need to think about what is actually happening to the curve when you get to those extremities. So what is actually happening is that so if I just do a quick sketch of the curve that we had, I think earlier. This is going to be absolutely awful, but I'll do my best. So it looks something like this. God, why am I doing this? I'm rubbish at drawing. You don't have to do the sound effects. Comes around and God. Right, that's not brilliant. It looks something like that. And at these points here, this one and this one, what is happening is that the x coordinate of the curve is changing from getting larger to getting smaller. In other words, the rate of change of x has gone from being positive, in this case, to negative. The rate of change of x. Well, the rate of change of x is the expression dx d theta. And the rate of change of x is large when the curve is up here, say, because look, it's going fast, the x is getting smaller quickly, but it's slow here. And it's 0 here. The rate of change of x is 0 here, because here it's going positive and now it's gone negative. So dx d theta equals 0 is the equation that we need to solve in order to find these two positions here. That's what we have to do, just solve dx d theta equals 0. Okay, well, I need to start then by considering an equation for x itself. Now the general equation for x is equal to r cos theta. Sip when we drink. X equals r cos theta. If you remember, when we started doing polar coordinates, we had 4 equations that link the polar and the Cartesians together, and one of those 4 equations was that x is equal to r cos theta. And so all we do now is we sub that in there. So we get x equals, in brackets, sine 2 theta plus 2 cos theta, like that. And all we need to do now so this is the value of x for any particular value of theta for our particular curve. So what we need to do now is to sub that into dx d theta equals 0. So I need to find dx d theta, I need to differentiate it. If I just rewrite it as sine 2 theta cos theta plus 2 cos theta, like that. I could actually immediately differentiate that now using the product rule for this, and that won't be a problem. However, it's going to be useful if everything's in terms of theta rather than having a 2 theta here. So I'm going to use a double angle formula, which again I'm not sure you've done yet. And the double angle formula this time, I mentioned the cos 2 theta double angle formulas. This one is the one for, there's only one of these, and that is that sine 2 theta, oh crikey, is equal to 2 sine theta cos theta. I'm going to sub that in there, and that's going to give me 2 sine theta cos theta times another cos theta, so cos squared theta, like that. Okay, right, I'm now going to differentiate this. So dx d theta is equal to, okay, so this is product rule, so I need to differentiate the sine theta and leave the cos theta alone. If I do that, that's going to turn into cos theta, so it's going to be 2 cos cubed theta. And now I need to differentiate the cos squared theta and leave the sine theta alone. So if I leave the sine theta alone, I'm going to get 2 sine theta, and then whatever the differential of cos squared theta is, which is going to be 2 cos theta times minus sine theta using the chain rule, and then plus the minus 2 sine theta on the end when I differentiate the cos theta. Went a bit quick there, so you might need to replay that a few times just to make sure that makes sense to you. Let's have a little bit of a tidy up. So what have we got? We've got 2 cos cubed theta, and then we've got minus 2 sine squared theta cos theta, and then we've got minus 2 sine theta, and all of that is equal to 0 at the point that we're interested in finding. So we need to solve this rather disgusting looking equation here, and in order to do that I need to get it all in terms of either cos theta or sine theta. Well, you won't believe how long this video has been paused for while Sir tried to solve this equation. Got there in the end and then realised it was wrong. I checked it on Desmos and it wasn't lining up. I had the wrong value of theta and therefore it wasn't the right tangent. Okay, so I spent ages and ages on this and I ended up with a tangent that just didn't quite make the grade. So what went wrong? Well, you probably know already. This is a 4, not a 2. There we go. Right, okay. So, first of all, can I just, a little disclaimer here. You're not going to get one like this in the exam. Way too difficult. The next bit is anyway, solving this equation. In fact, it ends up being a cubic, which doesn't have nice solutions, and so you need to know the cubic formula to solve it, or to use a calculator, which is what I did. Let's do it just for the sake of completeness, but like I say, if I'd have realised how hard this next bit was going to be, I wouldn't have taken this question on. But I've done it now, so let's go and try and solve this equation. What I'm going to try and do is write it all in terms of cos. Okay, so keep the first one the same, and then I'm going to eliminate this sine squared theta here by rewriting it as 1 minus cos squared theta, like so. Now, this is going to be a problem to write in terms of cos. I am going to get around that problem by introducing a square root in here, because sine theta is actually plus or minus the square root of 1 minus cos squared theta. Okay, but technically it's plus or minus that. I'm not going to overlook that. I'm going to change that to a plus or minus sign there. Okay, to take into account the fact the square root, and it could be either the plus or the minus version of the answer. You're going to see in a minute that ain't going to be a particular problem because I'm going to square it all back out again in a minute anyway. Okay, let's just tidy this up a little bit. So I'm going to get 2 cos cube theta plus another 4 cos cube theta and I'm also going to get a minus 4 cos theta. Like that. And let's just stick this on the other side, so it's plus or minus 2 lots of the square root of 1 minus cos squared theta. I know this would now be minus plus, but it doesn't really make any difference. Okay, both signs are there on the other side. Take out a factor of 2, combine these, so that would be 6. Take out a factor of 2 would be to make it a 3. So it's 3 cos cube theta, and then it's going to be this minus 2 cos theta is equal to the square root of 1 minus cos squared theta, plus or minus in front. So I've taken out a factor of 2 from everything. Right, now we're going to square both sides. I'm going to square this side and I'm going to square this side. So if I square this side, I've got to imagine it's in a bracket and square it. So I will get 9 cos 6 theta, don't panic, it'll sort itself out. And then I'll get minus 6 cos 4 theta, but I'll get 2 of them. So that will be minus 12 cos 4 theta. And then I'm going to get 4 cos squared theta here. And on the other side, I'm going to square it. And so the plus or minus becomes irrelevant now, because when you square it, it just goes back to 1 minus cos squared theta, like so. Oh, this is very exciting. Okay, now get it all on one side. So I've got 9 cos 6 theta minus 12 cos 4 theta. Then it's going to be plus 5 cos squared theta, take away 1 equals 0. And we have this lovely sextic, I don't know what they're called, order 6 polynomial. Well, we can't find the solutions to a 6 order polynomial ordinarily. However, this is the special case. Sometimes see these with quartics that turn into quadratics. As long as I've got even powers here, I can introduce a new variable, y, to stand for cos squared theta. Find a solution for cos squared theta, and then using this, find a solution for y, which is cos squared theta. And then once I know what cos squared theta is, I can find out what cos theta is, and therefore what theta is. Oh, I promise you this does work. You won't get one like this in the exam, but I'm kind of enjoying myself, so I'm going to keep going. So next step then is to replace all of these terms with y terms. So these terms with y terms. So I end up with 9y cubed, because cos 6 theta is y cubed, minus 12y squared, because cos 4 theta is y squared, plus 5y minus 1 equals 0, like that. Okay, so we've got a cubic to solve. It doesn't factorize, you can't do it that way, so we're going to have to use our calculator. So I've got my calculator here, and I'm going to, let's move this up. Here we go, you can all see that. So I'm going to go into polynomial solving mode, which I believe is number A. Polynomial, it's a cubic, and my coefficients are 9, minus 12. I don't know if you can see this. I know these don't come out very well on the calculator. It's 5. Just take my word for it if you can't see the calculator properly. I am typing in all of the correct coefficients, and I get an answer out there of 0 So if you can see that, 0.82185707773. I don't want to lose any of the accuracy of that, so I'm going to store that in A. So that's now stored in A, and I can come out back into normal calculator mode for the next bit. So I now know that y is equal to, let's just have another look what it was, 0.82185707773. There were two other values for y, but they were both complex, so I don't need to worry about that. So y was cos squared theta. So cos squared theta is equal to that. I'm getting messy now. Let's tidy up a bit. Therefore, cos theta is equal to the square root of that, which is going to be plus or minus whatever I get when I press square root on the calculator, which is 0.9065. Okay. Now, there are two values here. I haven't checked this, but I'm pretty sure that the negative one is to find this tangent down here. Okay, and if you proceeded with the negative one, that is what you would end up finding. But I'm going to ignore that just because it's not the important message that we're trying to give here. So I'm just going to use the positive version. That's cos. So if I want theta itself, make sure I'm in radians. I need to do cos to the minus 1 of that. So cos to the minus 1 of answer gives me 0.435725. Okay, so theta is equal to 0.435, but I'm going to store that in B. So that's now stored in B. Okay, so that is the angle, hopefully, that theta, that the point on the curve would be on. So if I could draw a half line on here on an angle of 0.43, whatever it is in radians, that should come out and hit the curve there, if we've done it right. Problem is that Desmos doesn't let you type in theta equals to get values. So I'm going to have to be a little bit clever to show you that this is in fact the correct value. What I'm going to have to do is I'm going to have to type in the x coordinate of that point, find the x coordinate of that point, and just type in x equals to show you that it's right on here. Okay, so what I'm actually going to do is I'm going to sub that value there back into x equals r cos theta. Okay, remember r is sine 2 theta plus 2 cos theta, like that. So if I type that in, that 0.435 into there, I'll get a value of x. Okay, so and it should be the correct value of x for the tangent to the curve that you saw a minute ago on the screen. So let's just try that. So it's sine of 2 beta plus 2. I hope you're still watching this. I've spent a lot of time on this. I've had quite a lot of fun with it. I kept messing it up. Didn't realise that 4 was wrong, which is obviously... what am I doing here? I don't want that in a bracket. Right, sine of 2b plus 2. And then I need to times that by cos of b. And I get a value. Okay, so that value there, which I'm just going to write it down here. I can't bother to store it. 2.506888784. Watch this. So here's the screen. Can you see the value there? Just about. Here we go. Here we go. So if I now type in x equals 2.5068874. Bingo. The tangent to the curve at that point. Right. I'm not going to do the horizontal one. I cannot be bothered, but the principle would be the same. If you want to take it on and really impress me, please feel free. I don't know if it comes out the same or not. The main difference is that when you come to do the horizontal tangent, it will be dy d theta that's equal to 0. It's the y coordinate that's reached a maximum. So this will be r sine theta. So when you multiply this out, you'll have a sine theta here rather than a cos theta. Whether that makes it easier, harder, I have no idea. If you want to try it, please feel free. Listen, this, what I've just shown you, way too hard really. But if you did understand it and enjoyed it, that's great. In any case, I'd like you to take on the exercise that I've set, which is I think it's the second exercise from the level 2 notes on the level 2 exercise from the set 2 notes of polar coordinates. I'll hold back on the assignment for now because I want to know how you find this and whether you understand it or not. It's been fun. See you next time.